Hello dear viewers, this is I, voice Gary, speaking to you as Buddy from Town's narrator.
I hope you are all in good spirits. So far, the Buddy from Town Space Exploration YouTube channel has covered some of the key stages, but not all stages, of the Big Bang for the very early universe. This included the Big Bang quantum singularity, the Planck epoch, grand unification epoch, electroweak epoch, symmetry breaking, and inflationary epoch and the rapid expansion of space. We then continued into the next video discussing the key Big Bang stages, not all of the stages, that included thermalization epoch, the quark epoch, baryogenesis, and hadron epoch. In this third Big Bang and its stages video, Buddy from Town will be working his way through the neutrino decoupling and cosmic neutrino background, CNEB, and possible formation of primordial black holes. First, neutrino decoupling and cosmic neutrino background. In Big Bang cosmology, neutrino decoupling was the epoch at which neutrinos stopped interacting with other types of matter, and thereby stopped influencing the dynamics of the universe at early times. Prior to decoupling, neutrinos were in thermal equilibrium with protons, neutrons, and electrons, which was maintained through the weak interaction. Decoupling occurred approximately at the time when the rate of those weak interactions was slower than the rate of expansion of the universe. As neutrinos rarely interact with matter, these neutrinos still exist today, similar to the much later cosmic microwave background emitted during recombination, around 377,000 years after the Big Bang. They form the cosmic neutrino background, abbreviated CNEB or CNB. The cosmic neutrino background is the universe's background particle radiation composed of neutrinos. They are sometimes known as relic neutrinos. Since neutrinos rarely interact with matter, these neutrinos still exist today.
They have a very low energy, around 10 to the minus 4 to 10 to the minus 6 electron volts, eV.
The neutrinos from this event have a very low energy, around 10 to the minus 10 times smaller than is possible with present-day direct detection. 4. Even high-energy neutrinos are notoriously difficult to detect, so the CNB may not be directly observed in detail for many years, if at all. However, Big Bang cosmology makes many predictions about the CNB, and there is very strong indirect evidence that the CNB exists. One of these predictions is that neutrinos will have left a subtle imprint on the cosmic microwave background, CMB. It is well known that the CMB has irregularities. Some of the CMB fluctuations were roughly regularly spaced, because of the effect of baryon acoustic oscillations. In theory, the decoupled neutrinos should have had a very slight effect on the phase of the various CMB fluctuations. In 2015, it was reported that such shifts had been detected in the CMB. Moreover, the fluctuations corresponded to neutrinos of almost exactly the temperature predicted by Big Bang theory, 1.96 plus or minus 0.02, compared to a prediction of 1.95 Kelvin, and exactly 3 types of neutrino, the same number of neutrino flavors currently predicted by the Standard Model. The next Big Bang stage is possible formation of primordial black holes. Primordial black holes are a hypothetical type of black hole that formed a mere fraction of a second after the Big Bang. Yakov Borisovich Seldovich and Igor Dmitrievich Novikov, in 1966, first proposed the existence of such black holes. Primordial black holes could have formed in the very early universe during the so-called radiation-dominated era. The essential ingredient for the formation of a primordial black hole is a fluctuation in the density of the universe, inducing its gravitational collapse. Some theories predict that primordial black holes should have popped early because in that fraction of a second after the universe itself began, space was not completely homogeneous, the same at every point. Instead, some areas were denser and hotter than others, and these dense regions could have collapsed into black holes. Depending on when exactly they formed, primordial black holes could have masses as low as 10 to the minus 5 grams, or 100,000 times less than a paperclip, up to about 100,000 times greater than the Sun. The theory behind their origins was first studied in depth by Stephen Hawking in 1971. The idea of such tiny black holes intrigued astrophysicist Stephen Hawking, who explored their quantum mechanical properties. That work led to his 1974 discovery that black holes can evaporate over time. While Hawking ultimately realized a large black hole would evaporate away in more time than the universe has been around so far, small black holes could have indeed evaporated away or currently be doing so, depending on their mass. Hawking calculated that any primordial black hole with a mass greater than 1012 kilograms, far less than the mass of any planet, dwarf planet, and most named asteroids and comets in our solar system, could still be around today, while those less massive would have already disappeared. Since primordial black holes did not form from stellar gravitational collapse, their masses can be far below stellar mass. Stellar mass is a phrase that is used by astronomers to describe the mass of a star. Primordial black holes belong to the class of massive compact halo objects, MACHOs. One way to spot MACHOs is by looking for events called microlensing, which occur when a massive object, like a black hole, passes in front of a more distant object, like a star or galaxy. The black hole bends the light from the distant source around it, brightening and magnifying the image. These events are infrequent and short-lived, but catching enough of them could allow astronomers to determine what the objects doing the microlensing are, and whether they could be primordial black holes. Primordial black holes are naturally a good dark matter candidate. They are nearly collisionless and stable, if sufficiently massive. They have non-relativistic velocities, and they form very early in the history of the universe, typically less than 1 second after the Big Bang. Depending on the model, primordial black holes could have initial masses ranging from 10 to the minus 8 kilograms, the so-called Planck relics, to more than thousands of solar masses. However, primordial black holes originally having mass lower than 1011 kilograms would not have survived to the present due to Hawking radiation. Hawking radiation is black-body radiation which is emitted by black holes, due to quantum effects near the event horizon. Because of this, black holes that lose more mass than they gain through other means are expected to shrink and ultimately vanish. Primordial black holes are also non-baryonic, and as such, are plausible dark matter candidates. Primordial black holes are also good candidates for being the seeds of the supermassive black holes at the center of massive galaxies, as well as of intermediate mass black holes. In March 2016, 1 month after the announcement of the detection by Advanced LIGO/Virgo of gravitational waves emitted by the merging of 230 solar mass black holes, about 6 times 1031 kilograms, 3 groups of researchers proposed independently that the detected black holes had a primordial origin. 2 of the groups found that the merging rates inferred by LIGO are consistent with a scenario in which all the dark matter is made of primordial black holes, if a non-negligible fraction of them are somehow clustered within halos, such as faint dwarf galaxies, or globular clusters, as expected by the standard theory of cosmic structure formation. The third group claimed that these merging rates are incompatible with an all-dark matter scenario and that primordial black holes could only contribute to less than 1% of the total dark matter. The unexpected large mass of the black holes detected by LIGO has strongly revived interest in primordial black holes with masses in the range of 1 to 100 solar masses. Regardless of where or how they're found, primordial black holes could tell astronomers a lot about the universe we live in. Depending on their mass, they could serve as probes into galaxy evolution, high-energy physics, and even the earliest fractions of a second after the universe was birthed. But, although primordial black holes could exist, they have yet to be seen, and currently remain one of astronomy's great questions. This concludes Buddy's video on the stages of the Big Bang, neutrino decoupling and cosmic neutrino background, and possible formation of primordial black holes. If you would like to follow along to see Buddy from Town become Buddy of Singularity, please click subscribe and a like would be appreciated. Until next time, dear viewers, keep looking up and looking back, way back.